last class, our first class, we talked about a bunch of stuff, including our syllabus, not in these slides. And we also talked about some states of matter. We talked about elements and compounds as two types of pure substances. Elements being any of our boxes on the periodic table, 118 options. It's more than enough options. And we've also got compounds. Compounds where we're mixing two or more elements together, and they're of fixed and definite proportions. If you change the proportions of the elements, it changes the compound. So it's a different thing. There's billions of combinations when you've got 118 elements, even though some of those don't exist right now. We also talked about mixtures. We've got heterogeneous and homogeneous mixtures. Our heterogeneous mixtures are not smoothly mixed, so you would have multiple different areas. So if you think of oil floating on the top of water, that would be a heterogeneous mixture. It separates out into two different zones. A homogeneous mixture is going to be something more like milk or soda. We've got multiple things in there, but it's a nice smooth consistency throughout. You can also separate mixtures. Not all mixtures are separable, but some of them, many of them are, and there's techniques that we can use to do those. So for example, a mixture of sand and water can be easily separated by decanting. Decanting is pouring off the liquid. We will be doing some decanting in our labs. This is also hopefully what you're doing if you wash your rice before you cook it. You're decanting, you're pouring off all the water, and hopefully you're getting some of the light solids out and keeping your rice behind. If you're not washing your rice, you might be doing something wrong. Another way that we can separate mixtures is by distillation or using a still. This is how they do like illegal alcohol purification, or illegal alcohol purification probably too. So with distillation, we're using heat to boil off or vaporize one of the components of the mixture. So this is a mixture of liquids. And so our apparatus would look something like this. We would have a mixture of liquids. We would apply heat, maybe not as directly as a Bunsen burner, and the more volatile compounds in this mixture are going to turn into a gas. We'll have capped the end up here, or you might have a thermometer up here. It forces the gas through this condenser, and this condenser has cold water running in from the bottom up through the top and then coming out again. And so this cold zone sort of acts like your windshield in the morning, and it collects moisture out of the air. So it's going to collect our more volatile component, which will then drip down into our collection flask. And we've got a little sidearm thing here just so that the pressure can be balanced. So we're not pressurizing this. This is part of how it works. So the one that more easily vaporizes is the one that's going to evaporate, turn into a gas, and be collected, and then the other things will be left behind. This is also how a lot of essential oil distillations are done, purifications are done. And some of those you can do at home, just not necessarily with this glassware, because lab glassware is usually kind of expensive. Another way that we can separate mixtures, if you have an insoluble solid, and a liquid, sort of like decanting, this is arguably better than decanting. So if we want to get all of the liquid out or most of the liquid out, we would use a filtration. So filtration, we're typically going to have a funnel. Sometimes it's going to be a flat bottom funnel, like a Buchner funnel, and we'd have a piece of filter paper sitting on the top. And we pour our slurry or our mixture of our solid and our liquid in over the filter. If we're doing this method, usually the filter paper is really fine, and so we're going to pull a vacuum below to pull the liquid through. And that's going to leave all of our solid hopefully trapped on the filter paper, and then all of the liquid filters through. This is also sort of what's going on when you do pour over for coffee. It's not exactly the same because we're extracting stuff out of the solid and it's already on the filter, but it's sort of the same idea. If you were to mix up the coffee grounds in the hot water and then pour it through the filter, you should achieve roughly the same results. It just might drain a little bit slowly, so you might end up with a weird extraction. Questions about any of those three separation methods. Cool, we can also go through changes. We've got two types of changes. Our first type of change is a physical change. A physical change alters the physical state. And when we think of physical states, you might think of states of matter. So solid, liquid, and gas being our three states of matter that we care about in this class. There's others. So if we're changing between physical states, then that would constitute a physical change. It could also alter the appearance. What we're not changing is the composition. So it's going to be the same chemical before and after. So whatever is in our substance is not going to change its identity during a physical change. Phase changes, changes between physical states, are always going to be physical changes. So if we heat up water on the stove, eventually it'll get hot enough, usually, that it will boil off, and this liquid water turns into gas phase water. Before it was water, after, still water. You could condense it out and you'd get your liquid water back if you really wanted to. So water before, water after, that makes it a physical change. We also have chemical changes, and a chemical change alters the composition of the matter. So for chemical changes, we're going to have different chemicals before and after. Different chemical, different compound, before versus after. So an example of this might be iron in a nail. We went to the hardware store, we bought some nails, and then we went home and we remembered, ooh, I've got to water all the plants. We left our little paper bag of nails outside the house. We woke up in the morning and it was all wet and soaked through, and some of our nails maybe got a little bit rusty. And that rust is a different chemical compound. One of the ways that we can tell, it looks different. So oftentimes there will be signs that we've gone through a chemical change. Some change in what it looks like, some change in what it smells like, some change in what it tastes. Hopefully we're not tasting rusty nails. But I imagine that it tastes different than a not rusty nail, which we also shouldn't be tasting. This would be another example of a physical change where we've got solid carbon dioxide, also known as dry ice, which you can buy at some grocery stores, sell it if you're 18 or older. You can have it in the solid form. And dry ice does something interesting where it doesn't actually go to a liquid phase at normal atmospheric pressure. And so the solid turns directly into gaseous carbon dioxide, which it can create some fun like party effects. So if you're hosting a Halloween party this fall and you want a spooky effect with your punch, you throw some dry ice in there and it makes a fog that comes out. Not ideal to like breathe a lot of it, but it shouldn't hurt you. And it looks cool. You can also do weird things like carbonating things that shouldn't be carbonated. Like you could, for example, you could take some milk and throw some dry ice in there and then close the container, hopefully not like a glass container because exploding glass is bad. And then you might end up with carbonated milk. And that sounds really awful, so if you try it, please let me know. I would love to see the results of that. I'm guessing that it's awful, so probably don't try it. And another example of a physical change is if we take solid sugar, like solid granules of sugar, crystals of sugar, and if you add that into a container of water, when you add it into the water molecules are going to go to work pulling apart the sugar molecules and separating them out. In our solution, we'll still have complete and intact sugar molecules. So before, we had sugar. After, still sugar. And so that makes it a physical change. However, it's not always a physical change when we are dissolving things. So one weird exception is if we're dissolving things like salt, things that are ionic compounds. that have positive and negative charges. We'll talk about those more later. When we dissolve those in water, water actually rips apart the positive charges and the negative charges. And so in solution, salt is different than it is in its physical form, which is kind of interesting. So ionic compounds dissolving is actually a chemical change because we've broken up the band of positive and negative charges. An example of a chemical change, anything burning. Propane gas is usually what you use for grilling outside. It is also what you would use if you go camping. Usually it's propane. Oftentimes it's marketed as liquid propane. It's what you get at like a gas station. You take in your cylinder and they give you a new cylinder, or you just buy a cylinder. It's propane in there. And when you burn it, it turns into carbon dioxide, CO2, which we exhale, and water. Other gases like methane will also go through the same combustion process. It's just a slightly different chemical reaction. So that would be an example of a chemical change. Before we had propane, and after we had carbon dioxide and water. So different chemicals before and after. Questions about our physical and chemical changes? Great. We also have physical and chemical properties which are related to physical and chemical changes. So a physical property is displayed without changing its composition. So it doesn't change the chemical. You can observe a physical property without transforming it into a different chemical. So for example, the smell of gasoline, if you go to Costco or whatever gas pump you prefer, and you're filling up your car and oops, you accidentally smell a little bit of gasoline, have you magically transformed your gasoline in your tank into something else? No, you haven't. Your gasoline is still intact, it's still good to be burned, your car's still gonna run. So that would be a physical property. So things like odor, what it smells like, taste, color, appearance, melting point, boiling point, density, those things are all physical properties. If you look at and observe the color of my shirt, it's roughly a mint green today. We've observed it. Is it still mint green? It is. It's a physical property. Color is a physical property. We can observe it without changing it. Some of these things like taste, usually if you taste something, there's some other changes going on, but taste itself is a physical property. Chemical properties are going to be displayed by changing its composition. So these can be observed with a chemical change. So if you want to observe these properties, you have to change your chemical. It has to undergo a chemical change. So like the flammability of gasoline, if you get some gasoline and you burn it, hopefully in your car, like in the engine, not in your, the cab, is it good to burn still? Once you've burned your gas, can you burn it again?
No, it's gone.
Unfortunately, no, it's gone. It's a one-time use commodity. You've observed the flammability, and now it's no longer flammable because it's turned into something else. You could also think of like candles. When you burn your candle, hopefully it's not your favorite candle. Once it runs out, it's gone. Buy a new one. Hopefully you can. Other things like corrosiveness, acidity, and toxicity are typically also chemical properties. They go along with chemical changes. A lot of things are toxic. They go into our body. They turn into something else because of our metabolism. It's beyond the scope of this class. It turns into something else, and that causes problems somewhere in our body. Okay, let's think about these 4 examples and whether the changes are physical or chemical and which type of property is demonstrated in each case. All right, we've got a copper wire, a little piece of copper, and we hammer it flat. that would be a physical change. It's still copper before and after. We've just changed its appearance. It's a little bit squashed now. So it's a physical change, and it's a physical property. That we've demonstrated. The malleability or the ductility, depending on what we're doing with it. Probably malleability. A nickel dissolves in acid to form a blue-green solution. This one would be a chemical change. And it would have demonstrated a property of the acid or of the nickel that they'll dissolve in each other. One of the signs that it's chemical, nickels generally are not blue-green. So if it dissolves into a blue-green solution, that's a color change. Color changes typically indicate a chemical change. Dry ice sublimes without melting. So sublimation, subliming, is when it goes from a solid to a gas. So what's that going to be? Physical. So this one's physical because we are just changing between states of matter. So we're changing from solid to a gas, which is a phase change. Phase changes are always physical. Yeah, sublime is going from a solid to a gas. And then how about D? A match ignites when struck on a flint. This one is also chemical. We've observed the flammability, which is a chemical property. Questions about any of those? Cool. The diagram on the far left represent liquid water molecules in a pan. Which of the three diagrams, A, B, or C, best represents the water molecules after they have been vaporized by boiling? It's going to be A. So in our original, right, our water molecules, they're one red dot, two white dots. In A, we still have one red dot, two white dots. They're a little bit more separated. They're not touchingly close anymore. So that would represent our gas phase, because they're separate. And it's the same unit. We've just changed the way that they're oriented relative to each other. In B, we've separated out the red and the white components, and so this is a different chemical. Our smallest unit has changed. So now we've got oxygen gas and hydrogen gas. And C, we've even separated those out even further. It's also different chemicals, but it's something funky. We've got atomic hydrogen and oxygen. So same chemical in our original versus in A, and that's what makes it a physical change. Questions at all about physical versus chemical? Cool. Scientific measurements. We're going to be making a lot of scientific measurements, mostly in lab. The way that we report scientific measurements is so that every digit is certain except the last. The last digit is always an estimate. The last number, the furthest right number, is an estimate. So there's a little bit of plus or minus incorporated into that last number. So a little bit of plus minus. depending on what instrumentation, what measurement tools you used to determine those values. So for example, we might look at the carbon monoxide concentration in LA County. Using one set of measurements, we might report it as 9.9, 9.0, 7.4, and so on. Using a different set of measurements, we might only be able to report it as 10, 9, 7, and so on. So the ones on the left, we've got more numbers. The ones on the right, we've got fewer numbers. We've just rounded all these numbers on the left to get the numbers on the right. So in our example here on the left, this 9.9, it could be a little bit below 9.9. So it may be 9.85, and maybe that rounds up to a 9.9. It could be 9.94, and that rounds down to 9.9. In our example on the right, this 10, there's a little bit of plus or minus baked into that. It could be maybe 9.5, or on the other extreme, it could be something like 10.4 would be our actual measurement. It's a lot more variability. 9.5 to 10.4 is a difference of 0.9. Over here, it's a difference of 0.09. So we've got a smaller grouping. These numbers here on the left are a little bit better because we've got more numbers. So the number of digits that we record depends on the measuring device. As scientists, if we're doing analog, like where we have to come up with the numbers, we're always going to read between the lines. I usually just refer to this as the estimate part. So on our measuring devices, if we look here at the bottom right, we've got a measuring device, and we've got this pistachio that was photoshopped in to be on the scale, because I don't think it was originally a pistachio. So there's this pistachio there. And if we look at our scale for the gram side, we've got markings every 1 gram, because we've got 10 grams here at the bottom right. We'll zoom in. Computer, enhance. We've got 10, and we've got 0, and we've got all the different subdivisions. So each of these smallest ones, we can count it up, is 1 gram. If we said that we have 1 gram, are we right at the 1 gram line? No. We're not. Are we at the 2 gram line? No. We're also not at the 2 gram line. We're somewhere in between, and we know that because we're looking at it, right? So we would know that we're somewhere between 1 gram and below that 2 grams. And so we would estimate 1 extra decimal place. So our measurement is between 1 gram and 2 grams. The next decimal place would be the 10th place. So usually what I say is, on a scale of 1 to 10, how far is it, or 0 to 10, how far is it from this first line, 1 gram, to 2 grams? And the number we're given from the book or whatever is 2 out of 10. You might read it as 3 out of 10. You might read it as 4 out of 10. 5 out of 10 is crazy. You might even read it as 1 out of 10. So there is some plus or minus built in here. So we would maybe read that as 1.2 grams. This is for analog, so like the clock in the back of the room, an analog clock. For digital, we don't have to do any estimating. We just take the numbers that we're given from whatever scale or clock or what have you. Okay, some practice. We've got a couple of things. We're going to try to record them to the correct number of digits. So our first one here, we've got a thermometer, probably in Fahrenheit. And so we're going to try to estimate, try to get a good reading of what this red line is. The red is measuring our temperature, so we're going to try to get a good reading of what's our temperature there. And in this second one, we've got water in a graduated cylinder, and we've got this curved meniscus. And we are going to estimate our volume from the bottom of the meniscus. So the meniscus is that curved part. There's also a meniscus in your knee, which also has curves to it. So we read off the bottom of the meniscus. So go ahead and take a moment, see if you can figure out, make a good guess about what those numbers might be.
Oh, right.
So let's work through picking some of these measurements. Hopefully you've got something written down, or at least set up in your mind palace maybe, so that you've got something to compare to. You get some feedback about I got it right or I got it wrong. Our first one, we're going to do the temperature. I'm just assuming that it's in degrees Fahrenheit. So we've got 100 here. That's too long of a line. That's our 100. This would be 110. We're definitely in between 100 and 110. We've got subdivisions between there. Our subdivisions, this would be our 5. And we've got 1, 2, 3, 4. It looks like we're around our 103. So that would be our 103. This next one would be our 104. It looks to me like we are a little bit past our 103. So we're locking in 103. It's definitely 103. And then there's a little bit extra, maybe, depending on how you look at it. Some of you might have seen this and been like, that is right on, it's spot on. If that's the case, then what you would report is 0.0. The 0.0 is very important because it lets other scientists know that you actually made sure that you did the estimate part. If you don't include this 0.0, then it looks like it's a less precise thermometer that you used. You might have also gotten 0.1, maybe even 0.2, and our units would probably be degrees Fahrenheit. So any of those three numbers I would be perfectly okay with. There's always a little bit of imprecision when we're doing analog measurements. For our liquid, we've got our markings of 4, and up here is our marking of 5. And we also have subdivisions. So we're definitely between 4 and 5, and we've got some subdivisions. This would be our 0.5. So this is our 4.5. The next mark would be our 4.6. We're somewhere between 4.5, but we're not quite to 4.6. So we would lock in 4.5. And then we do our estimate, 0 to 10, or 0 to 9, how far are we past this 4.5? And it looks like, to me, we're maybe 0.7, 0.8, somewhere in there. So it would be 4.5, and then we would guess maybe 7, maybe 8. And our units here would probably be milliliters. Questions about either of those readings? We will be doing a lot of such readings in lab.
Where did you get the 7, not like say 3 or 4?
So 7 or 8, because it looks to me like this line, the bottom of the meniscus, is more than halfway between this long mark and the next one, the 4.5, the 4.6.
Okay.
So it looks like it's more than halfway, and I'm just estimating it's maybe 7 or 8.
Okay.
Other questions? Cool. We also have the plague. Significant figures.
Oh, yeah. Yay.
So the precision of your measurement just depends on the instrument that you use to make the measurement. Some glassware, some instruments are very precise. Those usually cost a lot more money. Some are very imprecise, so they're not going to have very good measurements. And we can preserve that precision. We can demonstrate, we can retain that we used a really precise or really imprecise device with significant figures. So significant figures are significant digits. These are our non-place-holding digits, the significant digits, the important ones, in a recorded measurement. So it's going to be all of our certain digits and the estimated digits. The more significant figures that we have, the greater the certainty or the more precise our measurement was. And we've got rules, our first set of rules. How fun with significant figures. So for counting significant figures, here's some rules. So we've got rules over here on the left, and we've got some examples, and everything that we're talking about in the rule shows up here as a bolded number. So all non-zero digits are significant. So any number 1 through 9 is always significant. So in our 13.301, we've got 4 non-zero numbers. We've also got 1 0. Those 4 non-zero numbers are all significant all the time. Our interior zeros, so numbers that are between non-zero digits, are also significant. So this 0 that we had in our first example, the 13.301, this 0 is also significant because it's between 2 non-zero numbers. Leading zeros are not significant. They're never significant. So the ones that are in front of all the non-zero digits or numbers. A common point of confusion, saying that they're not significant is not the same as saying that we don't need them. We do still need them because these zeros let us know where our ones place and our other place values are. If we get rid of these zeros and we just write this as 2.3 or 23, that's not the same number, right? 0.00023 is very different from 2.3 or 2.3. So we still have to write them. It's just that they don't contribute to our measurement, our significant figures. Same for our other example. So if we have leading zeros, we still need the leading zeros. It's just that they're not considered significant. And then we've got 2 cases for trailing zeros. So trailing zeros are significant if there is a decimal point written in the number. So for example, 39.0, we wrote the 0 after it because we knew that we estimated that it was right at the 39 measurement mark. It wasn't 0.1 over, and it wasn't a little bit below either. So this is an important estimating number. Other examples, sometimes I would write like this 120. If it just had 3 significant figures, we could also write 120 period or decimal place, and that would also be a significant 0. And some instructors go different ways about implied decimal points, which is the next point. First question.
Is the 0 to 39 significant?
The 39.0? Yeah, that's also a significant 0 because it's after the decimal place. These are tricky sometimes because your calculator, if they're after the decimal place, your calculator likes to get rid of them because it thinks it's helping you by saving you space. But we need to be smarter than our calculator and know that we have to add those back in sometimes. If we have an implied decimal place, where our decimal place isn't written, like in the numbers 300, 238,100, 100,000, it's unclear, depending on who you ask, it's unclear if those zeros are significant or not. Some instructors would say that those zeros are significant. Other instructors would say just flat out they're not significant. It's safe to just avoid them. Questions about any of those?
So the 39.0 would have 3 significant.
Yeah, so 39.0 has 3 significant figures. We've got our 2 non-zero numbers, and then we've got our 1 trailing 0 after a decimal place, which is also significant. So that would be 3 sig figs.
What about the 120?
120.0?
That's fine.
This one would have 5. So all the zeros are significant because we've got a written decimal place.
And if there's no decimal place, what do you assume that the decimal
So if it was like this 300 and there's no written decimal place, it's at least 1. It could be as many as 3. Usually, when we've got trailing zeros like these bottom cases, it's best to write them in scientific notation. That's if we know how many significant figures it's supposed to have. If you're just given these numbers, then we would have to guess, because we don't know based on how it's written. We can also have exact numbers that don't fall into the significant figures category. So exact numbers have no uncertainty, rather, and so they don't affect the number of significant figures. We can basically think of them having an unlimited number of significant figures. So for example, exact counting of discrete objects, which is a very mathematical way of talking about that. Discrete objects, not things that you keep on the down low, but things that are like self-contained as like whole units, like pencils. How many pencils do I have? I have 2 pencils, but they're different sizes. It's still 2 pencils. It doesn't matter that they're different sizes. If you asked for a pencil and I handed you this really short one, I would have still fulfilled your request for a pencil. If I handed you the long one, that still counts as giving you a pencil, right? So I've got 2 pencils, even though they're different sizes. Nobody would dispute that I have 2 pencils, right? Nobody's going to say, you've got 2.1 pencils, Mr. K. You've got 1.5 pencils. I have 2 pencils. It's sort of the same with like students or apples or pennies. They often come in different sizes or shapes, but each of them counts as a whole thing. If I had 27.5 students in the classroom, somebody's getting arrested. There's always going to be a whole number of students in a classroom. So that would be discrete objects. Or maybe we could call those countable objects. Might be slightly different. Things that you can count in whole numbers, like students, pencils, apples. Some integral numbers that are part of an equation, like this 2 in diameter is 2 radius. That 2 is an integral part of the equation. So this 2 also has unlimited significant figures. It doesn't affect our number of significant figures. It's exactly 2 radii in 1 diameter. And we also have defined quantities. So like 1 gallon is defined as 4 quarts, or 4 quarts equals a gallon. Or other things like 12 inches equals 1 foot. Those types of things are exact. They're defined based off of each other, and so those also have this exact number, unlimited significant figures, quality about them. Some conversions are not defined quantities. Usually if you're in the same system, the English system, the one that we probably grew up with, versus the metric system, which the rest of the world uses and we'll be using a lot in lab. Usually if you're converting between those, it's not exact. Except 2.54 centimeters equals 1 inch. That is an exact conversion factor. It used to not be an exact conversion factor, but it was like 2.54, and then there were 3 zeros. And at some point, somebody was like, it's not going to change anything if we just make it exact. Can we do that? And they said, yep, sounds good. But like in big committees with people from all over the world. All right, let's practice. How many significant figures are in each number? We have 554 kilometers.
3.
We've got 3 significant figures. 3 SF. How about 7 pennies, RIP pennies?
1. 1.
Unlimited. Unlimited significant figures. because pennies are countable.
Oh,
/ discrete. So this is the same idea with the counting the pencils, counting the students, counting the desks. I just don't have 7 pennies to show you. So that would not affect significant figures. How about 1.01 times 10 to the 5 meters? This one is going to also be 3 significant figures. So we've got our non-zero numbers, and we've got an interior 0. So the interior 0 counts. This is scientific notation. We would never count this times 10 to the 5 part. That doesn't get counted for significant figures. How about D, 0.00099 seconds? This one is going to be 2 significant figures
the zero.
because the leading zeros don't count. We do have to keep them there, but they're not significant figures. What about 1.4500 kilometers? This one's going to be 5. We've got our 3 non-zeros, and then we also have trailing zeros with a written decimal place. Written Dr. Pepper. Okay, and then F, 21,000 meters.
Ambiguous.
It is ambiguous. Ambiguous. We've got at least 2, but maybe up to 5 significant figures. But definitely 2 because we've got 2 non-zero numbers. So if we were playing it safe with 21,000 meters, we would say that it has 2 significant figures. If we wanted to be more generous, we might say that it has 5 significant figures or somewhere in between. Questions about any of those? Cool. It seems like we've got a good grip. At least the vocal people have a pretty good grip on counting significant figures. We also get to use them in calculations. So in calculations where we're using measured quantities, it's important that our results, the numbers that we get out of our calculation, reflect the precision of the measured quantities. So oftentimes you plug numbers into your calculator, and if there's decimal places, you get like way more decimal places in your answer. And we need to know where to cut off those decimal places because we can't include all of them because then it would look like we've got 10 significant figures or something crazy. And that's usually not the case. So significant figures in calculations, we're looking at not losing or gaining precision, significant figures, when we're doing our maths. So first up, we've got rules for multiplication and division. Multiplication and division share the same rule because they're basically the same thing. So in multiplication and division, the result carries the same number of significant figures as the factor, the thing that goes into it, with the fewest significant figures. So we've got a couple examples here. Our first example, we've got 3 numbers that we're multiplying. Our first number has 4 significant figures. Our second one has 5 significant figures. And our third one only has 2 significant figures. This leading 0 is not significant. When we plug this into our calculator, we should get out 6.7208. And we're going to cut that off at the second significant figure. So then our final answer matches the same number of significant figures as our factor that had the fewest. In our second one, we're doing division. We've got 5 significant figures. We've got 3 significant figures. 3 is smaller than 5, and so we're going to round our final answer to have 3 significant figures. So that would be the second 6. So we would round at the underlined digit. I usually use this underline to mean that it's our last significant figure. This is especially helpful when we have multiple steps. So our last sig fig gets underlined. So that's for multiplication and division. We've also got rules for addition and subtraction. In addition and subtraction, we care about decimal places. Let me go back and write sig figs. So for multiplication and division, we care about number of significant figures. For addition and subtraction, we care about decimal places. A lot of the time this is numbers after the decimal. Sometimes it's numbers before the decimal. Usually it's after, so that's why we often count at fewest decimal places. So if you're actually adding or subtracting these, like we hopefully learned in elementary school, right, you're stacking them all up, it can be helpful to write a line after your number that ends the soonest. So this 0.07 only has 2 decimal places. So we write that line there, and that tells us where we round off. So we've got 2 decimal places for our shortest one. We had 3 decimal places for the top, 4 decimal places for that bottom one. You'll get a really different answer if you mix up your rules and you think that it's number of significant figures, because notice that this middle number, 0.07, is one significant figure, but the number that we end up with as our answer is 3 significant figures. So we're honing in on decimal places. We don't care about significant figures when we're doing addition subtraction. And then for this 5.9, 1 decimal place versus 3 decimal places, we're going to round off at 1 decimal place. And the arrow there showing what we're looking at to round up or down. So the fewest number of decimal places for our subtraction example is 1 decimal place, so we round our answer to 1 decimal place. Usually it's helpful to write these along when we're doing our calculations. Questions about either of our 2 rules? Yes?
If you're doing a problem with a bunch of steps, would you do the significant figures at the very end or like after each equation?
So if we have a bunch of steps, we're getting to that. If you've got a bunch of steps, you switch rules back and forth depending on how you're doing it. So like if we start off with some multiplication or division, then we would do number of significant figures, and that's where we would use that underline. So if we've got 2 significant figures, we underline our second significant figure. If we switch up and we're now going to addition subtraction, then we're going to switch rules. We're using decimal places now, and we would keep track of it just by writing the line under our last significant figure. It gets a lot more complicated when we switch things up. And then we would round at the very end, which we'll also get to. Okay, rules for rounding. When rounding to the correct number of significant figures, we're going to round down if the first digit dropped is 4 or less. This is also known as truncating. You just cut it off. So rounding for 2 sig figs, 24.4. The first 4 is our last significant figure. This would round to 24. So we're dropping the 0.4. We're going to round up if the first digit dropped is 5 or more. These are probably the rules that you learned when you learned rounding. Hopefully you've learned rounding before. So 24.5, we would round that 4 up, and it turns into 25. Something I looked into last semester, it's like, what if it's negative numbers? do you round up, like towards infinity, or do you use the same like number system? We're just always going to round. If we had a negative sign in front of these, we're going to round them the same way.
Same one.
So make the number bigger. So we're rounding away from 0 for these instances of 5s. It's probably not something that would have ever crossed your mind, but just in case you were curious, we're going to use that method for this class. It's important that the magnitude, the general size of the number, does not change like significantly when you round things. So for example, this number, $24,938.99, if we round that to 3 significant figures, our third significant figure is the first 9. We would look at the 3 that follows it to see how we round. How are we rounding? We're going to round down, right? Because the 3 is less than 5. So it would be 24,900. But we've got some ambiguous zeros. We know that it's 3 significant figures, so we'd have to rewrite this as the scientific notation form, which I believe is in my slides at some point. That's how we get around the ambiguity. So we know for sure we've got 3 non-zero numbers here. It's definitely 3 significant figures. It should definitely not turn into $249. $249 is very different from $24,900. Unfortunately, we can't exploit this. We can't change, like if we've got debt, we can't turn $24,900 into $249 by some cheeky small payments to get it to round out. So it's important that we retain the relative size of the number and not change things significantly. Some more rules for rounding. If we're rounding these to 2 significant figures, so 5.37, the 7 tells us we round up. 5.34, 4 is less than 5, and so it rounds down. 5.35, the 5 tells us that we round up, so it turns to 5.4. 5.349 still rounds down because the 4 is less than 5, so we're still going to drop the numbers after that. We're not going to pay attention to anything to the right of our first dropped digit. So this 9 doesn't, it's not important to us. This is a 4, so we round down. Questions about rounding? Cool. We also have multi-step calculations. So to avoid rounding errors are small changes that add up, that affect the final answer. So to avoid rounding errors, we're going to round only the final answer. Only round the final answer. One caveat here, reported values should also be rounded. So sometimes in our labs, frequently in our labs, we'll have a set of calculations that we're doing. We do like an addition subtraction at the start, and we're going to report that value in a table. When we report it in a table, anytime a number goes into a table, it should have the correct number of significant figures. If we use that number again later on, it's important that we use the unrounded number. I'll point out examples of that in lab when I can. So data tables, we should have rounded numbers. If you want to use the unrounded numbers, make sure that you at least put that underline so that we know what the correct last significant figure is. So if we are doing multiple steps, if we've got intermediate steps,
Can you not see table?
yeah, tables at the bottom. If you've got multiple steps, if you want to be a little bit lazy, then you can drop some of the trailing digits, and you probably are not going to affect things, at least 2 extra digits, 2 digits past your last significant figure. Part of the reason that I love my TI-36X Pro, other calculators can do stuff like this too, but you can, if you do a calculation and you want to come back to it later, you can just press the up key and it'll show you like the answer as well as the calculation. So you can go up and grab those really long numbers that sometimes get spit out. You can grab that whole thing in basically 2 button presses and then use that in your calculations. And when we get to that in lab, I might show you how to do that. If you have any calculator questions, please feel free to ask. I'm a calculator nerd. When in doubt, just include all the digits. So it's always safest to have everything. Okay, some multi-step calculations, or some calculations at least. We want to perform each of these calculations to the correct number of significant figures. In A, we've got 3.1-ish times 9.4-ish times 0.03-ish divided by 2.3 and some change. We're doing all multiplication and division. So it's all multiplication, division. What's our rule for multiplication and division? Anyone remember? Yeah, fewest sig figs. So
Operation, or do we just plug it in? Can we just
we don't have to do anything for order of operations because it's all multiplication, division. So we want to count up the number of significant figures that we have. For our first number, we've got non-zero numbers and we've got interior zeros, so they're all significant. We've got 6 significant figures. Our second one is all non-zero numbers, 4 significant figures. Our third one, these leading zeros do not count, and so we've got 3 significant figures.
set 3?
And then the last one, we've got 4 significant figures. So the smallest of those is 3 significant figures. So our answer should have 3 significant figures. So we'll plug in 3.1 and change. The other reason that I like this calculator is because you can plug in the numbers as fast as you want. Some other calculators will miss button presses. So the number that I'm getting out of my calculator is this. We want to round this to 3 significant figures. This leading zero is not significant, so we're starting to count at the 3, 3, 8, and then the 0 would be our last significant figure. We would look at the next number and only the next number to see how we round. 8 is bigger than 5, and so we're going to round up. So this turns into 0.381. And that would be the number that we would report. Questions about our first example? Yeah.
So for the ambiguous zeros, you only count them as sig figs when they're whole numbers, right? Not decimal numbers?
If it's in a decimal number, we've got a written decimal, and so any of our trailing zeros are going to be significant. All right, our second one, we've got addition and subtraction. We do addition and subtraction at the same time. What's our rule for addition subtraction?
Fewest
fewest decimal places. So we've got, in our first number, 3 places after the decimal. In our second one, we've got 1 place after the decimal. In our third, we've got 2 places after the decimal. So our final answer should have 1 place after the decimal. That's where we're going to round it. So put in our numbers. My calculator is telling me 120.961. We determined earlier it should have 1 decimal place, and so that's going to be the 9. Then we look to the next number to see how we're going to round it. 6 is greater than 5, and so we're going to round up. When we round up, we add 1 to the number. If you add 1 to 9, what does it turn into? 10. And so this turns into 121.0. That 0 is important because it retains our significant figures. So that keeps it at 1 decimal place. Occasionally, we'll have a couple of 9s stacked up. So we round a 9 up, turns into a 10, and then there's a 9 in front of that, and so that rounds up to a 10. That's okay. It's a little weird the first couple of times that we encounter it. That's normal. That's what we're supposed to do. We're not breaking any rules. Questions about our second? Okay, it recently came to my attention that maybe not everyone is learning order of operations in school, which is crazy to me, but that's okay. We'll talk about it now. So the general mnemonic device is PEMDAS. So we've got 4 different groups, and we're going to complete them in these orders. So anything that's in parentheses, P for parentheses, we're going to do first. If we've got exponents, we would do exponents after we do stuff that's in parentheses. So parentheses to exponents. And then we do multiplication and division at the same time. In math, they're basically the same operation. And then addition, subtraction gets done last. Which is frequently relevant for doing our problems. If there's no parentheses, or even if there are parentheses, right? If you enter C into your calculator, it'll spit out the correct, mathematically correct answer. It won't do the significant figures for you. So this is important primarily for significant figures, at least for this slide. Okay, so for C, we've got stuff that's in parentheses. We are going to do the stuff in parentheses first. What operation are we doing in our parentheses?
Addition.
We're doing addition. What's our rule for addition?
Count decimals.
Decimal places. So we've got 2 and 3 decimal places. So before we do the rest of it, we are going to do 44.11 plus 1.223. We'll get an intermediate answer. 45.333. With 2 decimal places, that means our middle 3 is our last significant figure. Then we can do the rest of the calculation. So we've got our multiplication and division. What's our rule for multiplication and division? Fewest number of significant figures. So this 45.33, we're now counting it for significant figures. It's got 4. Our middle number also has 4. It's a trailing 0, but we've got a written decimal place, so it's important, it's significant. And we've got 5 for our front one, same trailing significant figure, 0, whatever rule. So the fewest number, we've got a tie, it's for 4. So we're going to round our answer to 4 significant figures. So 2.511 times 21.2 divided by our previous answer. Calculator says 1.174270399. Always a good idea to just go ahead and write out all of the numbers. We'll learn a shortcut later, but for now, just write everything out. And then our fourth significant figure is going to be the 4. So 1, 2, 3, fourth spot, fourth significant figure. We're going to look at the 2 to see how we round. 2 is smaller than 5, so it rounds to 1.174. And then for D, in parentheses, we've got a calculation. We've got multiplication. What's our rule for multiplication? Fewest sig figs. So we've got 4 sig figs. And how many for our other one? 1, because we've got a leading 0. And leading zeros aren't significant. So we're going to put that into our calculator, 12.01 times 0.3. Our intermediate number, 3.603, we're going to have one significant figure. So the 3 is our only significant figure. It's important that we keep the rest of the numbers because it will affect the way that our calculation turns out. So one significant figure, but now we're changing rules. We've got addition. We're adding 4.811. And now we care about decimal places. We've got 3 decimal places in 4.811. How many decimal places are significant in our intermediate number? 0. This is one of those where calling it decimal places is a little confusing. None of the numbers that are after the decimal are significant. That's why it's 0 decimal places. So we're going to round to the ones place for our answer. So add to this our 4.811. Calculator says 8.414. Rounding for 0 decimal places or 0 places after the decimal, so that 8 is our only significant number. So this would round down to just 8. Questions? Cool. If you run into questions about significant figures during our lab, which is where I expect them to pop up the most, feel free to ask me. And that'll do it for today's lecture.